Welcome to part two of the lectures on the optical spectrum and remote sensing. Today in this lecture, we're going to be talking about color. The way we sense color with our eyes is we have three different types of cones in our eyes. Call them three different colors of cones. Implies that they have those colors. They don't. We have three different types of cones in our eyes. And what we have here is a graph, all right, of the sensitivity of each kind of cone to various parts of the spectrum. The visible spectrum spans from about 400 nanometers, right? That's 400 times 10 to the minus ninth meters in wavelength, up to around 700 nanometers in wavelength. It goes a little bit beyond that. So it spans this broad range. Um, the cones that we respond to blue light, we call blue cones. The cones that peak in the green area, we call green cones. The cones that peak here at 575 nanometers, we call those red cones because most of our red color vision comes from that set of cones, even though their peak is up at the edge of what we might call red. And so what happens in our brain, or in our eye? These cones are concentrated around the middle of the retina, where most of the images are going to be formed in our eye. And these cones, they're more green ones than anything else. There are actually very few blue ones. Our sensitivity to blue is pretty amazing, given how few blue cones there are relative to the others. Um, and so these cones receive, photons. Photons hit these cones, and what they do is they cause a chemical change in the cone. Now, for all of the cones in your eye, we have a threshold that you have to meet before they actually get activated. That threshold seems to be around 7 to 9 photons. In a later lecture, we'll talk about what that means in terms of energy, but 7 to 9 photons, somewhere in there, is where we are in terms of the amount of energy that needs to be deposited, right? Each photon represents a quanta of energy. And so you see these, your brain then takes all of this information on how much of a signal am I getting from the red, the green, and the blue cones, and puts that together into the colors we see. There are very fine mesh of them on the retina, so that also maps into a two-dimensional map. Then combining the left eye and the right eye, that maps onto a three-dimensional map. And our brain puts all of this information together. Another thing our eyes do is the cones actually do what we call integrate over a short period of time. And what that really means is if you'll imagine the amount of time in which the light hits the cone, it excites the chemical. That chemical doesn't de-excite right away. It doesn't get replaced right away. So it spends a little time excited. Well, another photon hits, then another bit of chemical gets excited, and this adds up the signal over short periods of time, depending on the activation time length of the chemicals in the cones. All right. If our cones did not do this, if we did not integrate light over a short period of time, you would actually experience movies as a series of still photographs. Right? You wouldn't actually see a movie. Your brain would not be integrating from one image to the another and smoothing out those transitions. And if you've ever seen a really inexpensively produced cartoon, it's down around 16 frames a second. At 16 frames a second, you can actually begin to detect the jumps in the image that take place as they go from picture to picture to picture. Because our cones integrate, we can actually have movies. If our cones did not integrate, we would not be able to have movies. We'd have a very different experience of films when we see them, and a very different experience of television. Um, the other thing is, because the cones put out a signal because a certain chemical in the cone has been excited, if you're looking at an image for a long time, or if you're looking at a very bright image, you can saturate the cone. When you saturate the cone, that means there's a period of time before it can recover and start seeing color again. Well, this absence of that color in the spectrum creates the negative image that you see and the after effect, right? So you have an after image caused by the depletion of these chemicals in the eye and in the cones. Um, you can get this by staring at any object for a long time and then staring off at something else, and you'll see the little after image. But it's particularly bad when you have bright images that deplete the cones to begin with. That's the other thing about our cones is they can saturate. And by that I mean they do get to the point where they adding more light does not make it look brighter. You you reach the limit of what the cone can actually see. Now, another good thing about the human eye is it's very nonlinear. So on the low end, it kind of starts off slow in terms of how much light it takes to get a response. And so you have to reach a threshold before you really start seeing a response. On the high end, it stops responding at some point. And so our eyes kind of compress the contrast a bit in the images we're seeing. And so when you look up at the moon's very bright. And we'll talk about CCDs in a minute. But when you look up the moon, you say, oh, gorgeous moon, let me take a picture. And you take a picture with your CCD camera on your phone. And when you look at the picture on your phone, the brightness of the moon washes out everything else. But when you look at it with your eye, it doesn't. The reason it doesn't is the CCD camera is much more linear across the intensity levels than your eye. The CCD camera doesn't suppress the bright light from the moon, while your eye, in fact, is suppressing the bright light from the moon and allowing you to have better contrast between the moon and the dark tree and or the shadow of the tree and the stars, whereas the CC doesn't just simply doesn't do that. The other thing we have in our eyes are rods. Now the rods are very sparse in the center of the eye, and there are more of them out around the edges. Um, the rods do not detect color per se, only in that because there's only one type of rod, there's no way to build up a color map from rods. Whereas there are three type of cones, you can build up a map of, oh, I've got a signal this big on green and this little on red and this size on blue. That makes this color look like, this color right here, right? Well, rods are either excited or not. All they detect is intensity because there's not a comparison between different types of rods. And they are much more sensitive than cones, about 1,000 times more sensitive than cones. Your rods are what you use for night vision, and also kind of like the cones, but much more so than the cones. They don't respond much on the red end of the spectrum. Now, here are the issues we have with rods. During the day, they saturate. In your office right now, they're saturating. When you're looking at this computer, they saturate. You pull up your cell phone to read email, they saturate. After saturating, it takes about 30 minutes for them to reach their full sensitivity in dark. So if you're outside at night and you're trying to see your way around, as soon as you pull out your cell phone to check text messages, you're doing away with your night vision and you're 30 minutes away, probably 30 minutes or so away from being able to see well in the dark again. So if you want to see well in the dark, you need to stay in low light conditions. Don't pull out your phone. Don't pull out a flashlight. Right? A flashlight's going to interfere with your ability to see everything else other than what's in the beam. Um, so your cones are much more sensitive. They saturate. It takes a long time for them to recover. Um, and they're a primary source of night vision. The other thing about cones, because there are more of them around the edges of the retina, around the edges of the image, than there are in the center, you will sometimes notice under low light conditions you'll see something out of your corner of your eye, but when you look directly at it, you cannot see it anymore. And the reason is around the edges we're more sensitive because the predominance of cones around the edges and the sparsity of cones in the middle, right? You can actually see, let's say you're out at before dawn hunting, you can actually see a deer out of the corner of your eye, but when you look at it, it disappears. You can see stars at night out of the corner of your eye, but when you turn to look directly at them, they will disappear. Some of the dimmer stars, you can see them out of the corner of your eye, but not when you look at them directly. Right? So we have these two different types of detectors in our eye. Um, and these two different types of detectors let us see either color or simply intensity, and they help us span from daylight to nighttime. The other thing you'll notice in these diagrams is there's a hard cutoff, right? There's a hard cutoff here. The reason there's a hard cutoff here is simple. Um, our cornea cuts off ultraviolet light and prevents it from entering the eye. So the blue cones are actually sensitive to ultraviolet light, but it simply doesn't get there. It doesn't get all the way to the retina. It's blocked way before it gets to the retina. Well, there are some people that have a defect in their eyes where they do not have the pieces that block out ultraviolet light. These people can actually see into the ultraviolet, and they describe it as a bluish white color when they see up into the ultraviolet, right? So they can see down, you can imagine this line just continuing to come down. They can see in there. And so it's not a matter of our cones can't, it's just a matter of we have a filter on our eyes that cuts off that end of the spectrum. All right, and ultraviolet light, shorter wavelength, higher energy. There are good reasons for not wanting it in your eyes. There's a good reason for wearing UV blocking sunglasses, but that's the nature of this end of the spectrum. The other piece in this spectrum is there is a fraction of the population that sees a fourth primary color that we believe sits right in here between red and green. My son's mother was one of these people. The upshot of that is there are several things. One, she was hired by people to mix paint for their homes because she could look at the paint on the wall and exactly match the paint in the mix that was going to match the paint that was already on their wall. And by this was when we were on Long Island, and so she was hired by people with multi-million-dollar homes to do this. Um, the other is she and I could never agree on what color something was, right? And we couldn't agree on what color something was because her perception of color was fundamentally different from mine. And her perception of color is fundamentally different because she sees four primary colors. Just like if you're talking to someone that can't see blue, then you can't agree with them on what color something is if they can't see blue or if they can't see red. You can't agree with them on what color something is. So people that are colorblind see a completely different world from those of us that are not. Final bit on color and the human eye. Blue, you'll see how much farther out it is, and the fact that blue is very sparse. Blue cones are very sparse in the eye relative to the others. Um, this prompts some questions about how long have we been able to see blue, because when we read ancient literature, there is no word for blue. Homer talks about the gray sky, and Homer talks about the wine dark sea. He never talks about the blue sky. He never talks about blue sea. The word blue, there is no word for blue, pardon me, in a lot of the ancient literature. So blue may be a relatively new thing for us. Okay, now that we're done talking about color in the human eye, let's talk about color and CCDs. Because CCDs are what we use most of the time for taking color images now. We rarely use film. I'm not going to talk about film here. I'm just going to talk about CCDs. Um, a CCD, a charged coupled device, is an array of tiny squares or pixels. When a photon hits one of those, it causes charge to be deposited on a collector, right? Like the human eye, the CCD will continue to collect charge, continue to integrate the image until you decide to read it out. So, unlike the human eye, when we don't get to pick how long we spend reading out or how often we read out the cones, with the CCD, we get to pick. And because we get to pick, We get to pick how many frames per second we do with a CCD. Um, there are very fast cameras that will do 1 million frames a second, and they can capture things happening very quickly, and then you can slow it down and look at it. Our our in astronomy will actually take a CCD camera and use it to see something very dim, and point it at an object for 30 minutes at a time, and not collect the electrons off of it for up to 30 minutes. And so what we see is the image added up over 30 minutes. The other thing about CCDs is they are much more linear. So with a human eye, the first photon to hit doesn't have much effect. The second photon doesn't have to have much effect. So you need to get up around 7 or 9 photons before you're beginning to impact the image in the human eye, hitting a single cone. Well, for CCD, the first photon impacts the CCD and creates a charge. The second one creates the same amount of charge. The third one adds the same amount of charge. And so CCD is much more linear. Back to my discussion about the moon, the CCD doesn't depress the brightness of the moon. It doesn't increase the contrast in the image. That's something that you have to take care of after the fact if you want to be able to see the image that you saw um, with your eye when you looked at the moon. And then with CCDs, how do we see color? Because the CCD itself isn't sensitive to color. Well, the way we see color with CCDs is we put a mask over it, a filter. And the filter has twice as many, and the colors here are actually misleading because the green is definitely not green. That lets green pass, right? So we end up with twice as many green sensitive cells as our blue or our red, right? Because we do um, 2 greens, a blue, and a red, right? And we do this just because we're trying to mimic what's going on with the human eye, where we have more, not only do we have more green um, cones, but green and red overlap in here, and so we see green easier than we see the other colors. And you'll often notice as low light conditions happen outside, things will start to look a little green. You'll notice as low light conditions happen in the clouds, like bad weather is coming in, things will start looking a little green, and that's a function of the low light conditions and the fact that what we're left seeing is green. And the reason we do this is we're trying to mimic the human sensitivity across the spectrum. Now, we don't quite get there. A CCD image, if you look at it carefully, doesn't quite replicate what you see with your own eye, but we get close, right? And so part of this for you to understand is when you're looking at color, right? We process color in one way with our eyes. We process color another way with CCDs. When we replicate that, you have to be aware that there are differences. That when we're looking at an image, color is not exactly what we would call color, but color is a construct within our own eye, our own head, in the processing in the brain, in the occipital lobes. The other thing about color that you need to understand is that color is in large part a function of when we see color, we are thinking of photons adding up to give us a color. When we're looking at things that have color, we're looking at the colors that we're reflecting off of them. And the color that we perceive an object to be depends on the colors it does not absorb. I once upon a time had a pair of sweats. They looked red and they looked like they matched the top and the bottom. All right. And if you had me out in daylight, they looked perfectly like a perfectly matched set of sweats. Well, I purchased them separately. All right. And so one of the things about the color we perceive something out as depends on the light hitting it and what it absorbs. Part of that depends on what's the source of the light. So when I went out in the sun is line A here, right? There's a broad spectrum. And there's enough red, and red is pretty flat across that spectrum. And so the top and the bottom looked red. Or under fluorescent lights, where across the spectrum, fluorescent lights are pretty not constant, but there's a contribution everywhere. It's not bits and pieces. They would look red. And you'll notice here, one of the reasons fluorescent lights often look bluish is because of this big peak right here. You can buy fluorescent lights that actually mimic the sun a bit better, and if you buy those, they're expensive, but if you buy those, you'll notice that makes it feel much more like you're outside when you're sitting in fluorescent light that mimics the sun. I did this in a kitchen of mine once upon a time, and it made the kitchen feel much better, right? Because it was much more like sunlight than fluorescent light. See, fluorescent light, this big blue peak, and then this green yellow bit in here. Sunlight, much more blue and flatter across the rest of the spectrum. Incandescent light appears yellowish because of its emission. It's and yes, it's much more intense over here in red, but we're not very sensitive over here in red. So incandescent lights, which are going away, incandescent lights appear more yellow. And then there's something like helium neon, which you see in, signs where you got a bright red. Well, these sweats I was talking about, when you take them out under the sodium lights in street lights at night, the sodium lights emit specific frequencies, much like helium neon, and because of that, the top, and I discovered then the top and the bottom were actually reflecting slightly different reds, and the top, the red in sodium was reflected off of red and sodium lights was reflected off of the top. So in sodium lights, under street lights, these red sweats I had, the top looked red and the bottom looked black. And the bottom was looking black because it absorbed everything else and it didn't reflect the particular narrow line of red that the sodium lights were emitting. And so when you're looking at anything having to do with color, you have to be aware of several things, right? You have to be aware of your sensitivity to color, and you have to be aware of what colors are being emitted, but what's your light source, right? What's the light source for you to use to see color? And we're of course tuned to the sun because that's what we use most of the time. And then you have to be aware of what is the object that I'm looking at actually reflect, right? Because like my sweats, you can move off of the red that it reflects just a little bit and suddenly it goes black, all right? Suddenly we're off into a part of the spectrum where all the light's absorbed. All right, that's it for part 2. I'll talk to you later.